Hey everyone, in this video we're going to be looking at how area models can be used to represent fractions. So area models are used to depict the parts of a whole way of representing a fraction, and the denominator of the fraction determines how many equal-sized pieces the whole shape is cut up into, and the numerator of the fraction represents the parts of the whole that are being highlighted, which is usually represented with shading those parts. So when we're using area models to represent fractions, the shape doesn't matter as long as it can be partitioned into pieces of equal area. For example, the fraction 1/6 can be represented by all three of these area models. However, some shapes are easier to partition than others, depending on their lines of symmetry. So circles and rectangles tend to be really easy to partition, and regular polygons, which are shapes that have an equal side length on all of their sides, can be easy to partition if the number of sides either corresponds to the denominator or half of the denominator of the fraction. For example, if I wanted to model the fraction 5/12, I could model it really easily with rectangles or circles, and I could also model it easily with a hexagon because I could partition this hexagon into 6 equal-sized triangles because of the lines of symmetry on this hexagon. And then once I have my 6 triangles, I could cut each one of them in half to form 12s. And so this shape could be easily partitioned into 12 equal-sized triangles, and then I could shade 5 of them, like this. However, it would not be very easy to partition a pentagon into 12 equal-sized pieces because there's only 5 lines of symmetry instead of 6. But it would work well to partition a pentagon into fifths because I could split it up into 5 equal-sized triangles. Or I could also partition it into tenths because I could take each of these triangles and split them in half. And so with regular polygons, the number of sides should correspond to either the denominator of the fraction or half of the denominator of the fraction. And when you're teaching students about fractions, you can use all sorts of physical objects as area models. For example, when I was learning about fractions, my mom used graham crackers to help me understand that 1/2 is more than 1/4. You can also use paper folding, various types of blocks, and things like egg cartons to let students physically partition wholes into parts. And when you're using any type of area model, it's important to define clearly what the whole is. For example, if you're using fraction blocks to represent fractions and you define the yellow hexagon as being the whole, and the red trapezoid blocks are halves, the blue diamonds are thirds, and the green triangles are sixths. But the green triangles would be halves if you define the blue diamond as being the whole, and they would be thirds if you define the red trapezoids as being the whole. Similarly, if you were using Legos to represent fractions, the 2x2 block would be 1/5 of the 2x10 block, but it would only be half of the 2x4 block. And if you were using eggs to represent fractions, 3 eggs would be a sixth of an egg carton that holds 18 eggs, while 3 eggs are also 1/4 of an egg carton that holds 12 eggs. And they would be a half of an egg carton that holds 6 eggs. And by discussing issues like these with your students, you can help them understand that fractions are only comparable if they're referencing the same whole. For example, a half of a large pizza is not the same thing as half of a small pizza. And you can also use physical models like this to show equivalent fractions, because in the egg carton example, 3 out of 18 eggs be represented by the fraction 3/18, but it is also 1/6 of the egg carton because you could split the egg carton into 6 equal-sized pieces, and those 3 eggs equal 1/6 of the egg carton. So the key concepts that are important when using area models are first, that the whole is well defined, and second, that the whole is partitioned into equal-sized pieces. So it's often easiest to draw the equal-sized pieces as congruent shapes, but they don't necessarily have to be congruent. For example, if we use this large square to represent the whole, both the yellow shaded part and the purple shaded part both represent 1/4 this large square, even though the yellow part is a long, skinny rectangle and the purple part is a smaller square. Because the area of the rectangle and the square is the same, the pieces are considered equally sized. So I hope this video was helpful for you, and I hope you have a good day. If you have any questions, let me know.